Okay, so in this section, we want to explore what is called graph coloring. So, quick definition. A vertex coloring of a graph is where we color each vertex some color. The color may be the same for every vertex, or we may use a different color for each vertex. So if I wanted to color each vertex the same color, say red or blue, I could. Or if I wanted to use a different color for each vertex, maybe I had a graph with 4 vertices and I wanted to use 4 different colors, then I could do that. Okay? Now, this is important. If we color the graph in such a way that no 2 adjacent vertices are of the same color, the graph is said to be a proper coloring. So it is a proper coloring if no 2 adjacent vertices are the same color. Now, definition. Let G be a simple graph and K be a natural number. The least K such that G is K vertex colorable is called the chromatic number of G and is denoted by CHROM, and this is simply read chromatic, G. In essence, the chromatic number of a graph is the smallest number of colors, the minimum number of colors needed to perform a proper coloring. So let's do an example or several examples. Determine the chromatic number for the following graphs. So let's take a look at K4. So if you remember, what did K4 look like? I could draw K4 as follows. Like so. Try to make these vertices a little bit bigger. So I'm going to now color this graph. And let's color it this way. So here is this first vertex. Now, what I have to do is I'm now going to go to another vertex. Let me just label these V1, V2, V3, and V4. Now, I cannot color V2 the same color that I did V1. So how about I color him green, like so. Now I'm going to slide over here to V3. Well, V3, since V3 is connected to V2 and V1, I cannot color him green or red. So how about I color him blue? Now, I have one other vertex, V4. Well, notice V4 is going to be connected to V1, V2, and V3. So I cannot color V4 red, green, or blue. So let's color him perhaps orange. And so if you notice right here, we have done what is called a proper coloring of K4 in such a way that no 2 adjacent vertices are colored the same color. So we would say the chromatic number for K4 is in fact 4. Why? It took me 4 different colors, red, green, blue, and orange, to color these vertices. Okay, let's slide down and take a look at this next graph right here. Okay, I don't know if this graph has a name per se, but let's take a look at it. We'll just call him G. Okay. Now, we can label these vertices however I want to, but I'm going to begin to color this graph. So I'm just going to start here with the bottom left. This guy is going to be red. So the 2 vertices that touch him, I'll just call him possibly V2 and V3, I cannot color them red, and I cannot color them the same color because they touch each other. So how about I color one of them green, and the other I will color blue. Okay. Well, this one is blue. He's incident to this vertex right here that's colored green. I can't color this guy green, but I wish to try to use the minimum number of colors as possible. So I'm going to slide up here to this next vertex and color him red. Well, if I've colored this guy red, this one over here green, I would like to color this one, and I want to try to use the minimum number of colors as possible. So I'm going to color him blue. And now let's slide down to this last vertex down here. You guessed it. What color am I going to color him? I'm going to color him green. Now let's take a look. Each vertex, for any vertex that is adjacent to him, it is colored a different color. For instance, this vertex right here, I'll just call him V1. He's connected to a green and a blue. Well, what about this blue down here? I might call him V2. He's connected to a red, a green, a red, and a green. So notice he's not connected to any blue. And so I've colored this in such a way where no 2 colors touch. And so I would say the chromatic number of this graph G is 3, because it took me 3 different colors to do a proper vertex coloring. Okay, let's slide down and take a look at another graph. This next graph is a very common graph in graph theory called the Peterson graph. It's more or less a pentagram inside of a pentagon. I have this pentagon, and then inside of it I have this star or this pentagram, and it is attached or connected to the outer pentagon. So let's do a proper coloring. Okay, so how would I color this one right here? I'll start with orange. So if I start here and I color this vertex orange, then let's slide upwards and color him a different color. How about I color this one green? But if I color him green, then I could, if I wish to, color down here green. Okay, well, let's continue. If this up here is green, and I want to come down to the left on the pentagon side right here, I need to color this guy. I can't color him green. So what about blue? Like so. And I'm going to color this one down here orange, because I can't color him green or blue. So notice at the moment I've colored the outer pentagon and no two colors are touching each other. Now, let's color the pentagram on the inside. Okay, so if this one is green, then let's connect him on the interior with an orange, like so. Now, if he's orange, this guy right here can't be orange. So how about I color him, we'll say green, and then I'll color this one green, and then I'll color the remaining two blue. Now, let's take a look at this. Okay? If I look carefully, no two adjacent vertices are the same color. Okay? Switch to black. If I just call this V1, green to blue to orange, and that's okay that I'm going to orange twice, I'm just not going to a green. What about a different vertex? What about this guy over here? I'll call him V2. My claim is that this orange one is not connected to any other adjacent oranges. There's a green, and a blue. So my claim is that no two adjacent vertices are the same color. So let's count how many different colors did it take for me to color this graph. Well, 3. So the chromatic number of the Peterson graph is 3. Now, let's slide down here, important. To what is called the four-color theorem. The four-color theorem. If G is a planar graph, okay, so we have to remember what a planar graph is. That means I can draw the graph in the plane where no two edges cross each other. Think example K4. What did K4 look like? This is our new favorite graph. It looked like this right here. Okay. If I have a planar graph, then the chromatic number of G is less than or equal to 4. This is why this is called the four-color theorem. That is, if G can be drawn in the plane in such a way that no two edges cross, then the chromatic number is at most 4. It puts a cap or a ceiling on the maximum number of colors needed to do a proper coloring. So let's continue and take a look at an example. The graph below is planar and thus has a chromatic number of at most 4. So this graph right here with all of these triangles right here, it's planar. I can draw it in the plane in such a way where no two edges cross each other. And so notice the chromatic number is in fact 4, but it puts a cap on it. It puts a ceiling on it. Now, below is a graph of the United States. Since the graph is planar, meaning I can draw it in the plane with no edges crossing, the chromatic number is at most 4. So let's quickly, I don't know if it'd be quickly, but let's do a chromatic coloring of this graph right here. So I'm going to color this as follows. So down here, I have the actual map of the United States, but as a graph, I have it right here above. So let's color as follows. So we could do Maine, Vermont, Connecticut, New Jersey, Maryland, North Carolina, Florida, Kentucky, Michigan, Iowa, Louisiana, Oklahoma, Wyoming, North Dakota, Arizona, and Oregon, all as green. Now, let's color in as follows. Let's say I did red, New Hampshire, Rhode Island, New York, Delaware, Ohio, Virginia, South Carolina, Alabama, Illinois, Arkansas, Kansas, Minnesota, Montana, Utah, New Mexico, Washington, and California. So notice, no two greens are touching each other, no two reds are touching each other. Okay, now let's do a different color. Maybe here. Okay, Massachusetts, Pennsylvania, DC, Georgia, Indiana, Wisconsin, Missouri, Mississippi, Texas, Colorado, South Dakota, and Idaho. Notice still, no two colors no two states or no two colorings are adjacent to one of the same coloring. So that leaves a fourth color for the remaining states: West Virginia, Tennessee, Nebraska, and Nevada. And so we just did a proper coloring of the United States map. My claim is if you pick any state, I can color it in such a way that each other state next to it is drawn using a different color than that state. And it took at minimum, if we count, 4. And so the chromatic number of, I guess I will call this the United States graph, is 4. This graph is planar because I can draw it in such a way that no two edges cross each other. In essence, the vertices themselves are the states, and the border between respective states is an edge that connects one state to another. And so we can view the United States map in a mathematical sense as a graph whose chromatic number is 4. And that will conclude our discussion on graph colorings.